right, ladies and gentlemen, class recording for today has started. So, last unit, we started dealing with mechanics. And we said when we were looking at mechanics, we are looking at what? Mechanics is our study of what? Movement, motion, okay. So, mechanics is our study of motion. And in measuring the motion of an object, we said there were 4 questions that we want to answer. Yes? Do we remember the 4 questions? No. Kinda, sorta? All right, what's the first question? Where's the object? What's it doing? What's it going to do next? And that's the first one, where, right? And then when, right? So we introduced in the last unit position, velocity, acceleration, right? We talked about how they're all connected to one another, how change in one can affect the other ones. We went all through there. But there is one question that we haven't answered yet. And that question is, what is like velocity, right? Okay. There's another W question that we haven't answered yet. Why? Why do all of these things happen? And the answer is force. So, what is a force? Again, force is one of those terms that I'm pretty sure all of you know, pretty sure all of you have used, and if I said, hey, use it in a sentence, you probably could use it correctly in a sentence. But when we're using it to analyze motion, when we're using it to explain motion, we want to stick with a very specific definition. First, a force is a push or a pull, which isn't very specific. All right? It's very general and kind of more of a, oh yeah, duh, kind of an explanation. But more important to our discussion and our use of forces to analyze the motion of an object is that forces cause acceleration. Forces cause acceleration. And in the last unit, we introduced the concept of acceleration, right? We said that acceleration is what? Change in velocity. So there's 3 things that we talked about could be acceleration, right? Speeding up, slowing down, changing directions. If any one or more of those things happens, force is required. Forces cause things to change what they are doing. Forces cause things to change what they are doing. Next, force is a vector quantity, meaning it has to tell us direction and magnitude. Oh yeah. So in this case, right, the magnitude part is how big is the force? How strong are we pushing or pulling? But then we also need to know which direction we're pushing or pulling. Because the same force or the same magnitude force could have different effects on an object depending on how we push or pull it. If something is moving to the east and we continue pulling it towards the east, it's going to speed up. But if something's moving towards the east and we pull it to the west, we may be pulling it just as hard, but based on the direction, a different type of acceleration will occur. Right? So forces are vectors. What will happen as we move along here in this unit is we will see that very seldom can we analyze what's going on with the motion of an object by only looking at one force. A lot of times we have to look at the combination of several forces. When that happens, it's best if we draw a picture that shows all of those forces. Arrows make a very convenient representation for forces because they can show us which direction the force is acting, but then also how big it is depending on how long the arrow is. Good there. There are two ways in which we can cause an object to accelerate. The first way that we can cause an object to accelerate is called a contact force. And like its name suggests, we have to contact something. These are what most of you would give me as examples of forces. Your pushes and your pulls and your hits and your throws and those kinds of things. But we saw in the last unit that this can happen, right? And we talked about that is acceleration, right? Free fall acceleration, and it can do it on the way up and the way down and all those fun things, right? This is accelerating, but there isn't anything actually contacting it. Because another way that forces can work is by something that we call a field force. We have discussed field forces before. All right? We introduced the concept of field theory back when we were talking about electricity. Do you remember who developed field theory? Who's responsible for the idea? Faraday. Michael Faraday. But in examining what Faraday proposed when he was talking about electricity, we can also apply that to magnets and gravity, right? Any of these things that can cause an object to move without actually touching it. We refer to them as field forces. This next part isn't on your outline, but it's kind of a review of some things we talked about, right? We talked about the concept of a force field, right? We said the force field is an area that surrounds an object where it can affect other objects, right? We live in the gravitational field of the Earth because Earth's gravity can cause this to happen, right? The field is an area that surrounds something where it can affect other objects. And as we move farther and farther away from something, its field strength decreases. So the farther we are away from the Earth, the less ability it has to cause this object to accelerate. Right? Good there. Okay. Let's talk next about, pictures, right? The one on the left, obviously representing a contact force, and I think you guys have that picture right there. And the one on the right, representing a field force, and I always tell myself when I use this picture of the cliff diver, yeah, he definitely cleared those rocks down at the bottom, right? So, just because I don't want to feel bad about showing you guys a picture of impending doom. So yeah, he totally cleared those rocks, totally. So. Yes, Julie.
For the picture on the right.
Yes.
I mean on the left.
Wait.
On the left. Does that have to do with the scenario we talked about how he's performing work?
Right. We said, remember that our definition of work was a change in the energy of an object, right? Does that sound familiar? In order to make the energy of an object change, you need force. Forces cause things to change, right? That's basically kind of tying it back together. We didn't really know what force was back then. Now we look at it more generally, but yeah, same idea. That's why we need force to do work, because in order for work to happen, an object has to change what it's doing. So, okay. Wow, look at that connection. Connections all the way back to like September. So, yeah, so I mean, and check out all those lines of back force, man. That's like 4 lines of back force. That is. Oof. No. Look, he's got a belt on. It's good. It's all good. So as long as you have a back brace on, you can lift improperly. It's okay. It doesn't, you know. All right. So measuring force. Force is measured in a unit that's called the Newton. And if you can't figure out where its name came from, wait till tomorrow. You'll find out then. Okay. Yes, figs. We're having fig Newtons in class tomorrow. It's on recording, so obviously you can't put anything on the internet that's not true, right? So, just kidding, everybody. No, well, I'm not bringing fig Newtons to class tomorrow. Somebody else wants to bring fig Newtons, you know. I'd accept strawberry or blueberry Newtons as well. Just so. All right. By definition, 1 Newton is the force required to cause an acceleration of 1 meter per second squared on a 1 kilogram object. Yeah. We'll talk about it. So first, hopefully you can tell from the definition of what a Newton is a derived unit, right? Because it deals with meters and seconds and kilograms, all kinds of things, right? We have to measure, we have to make several individual measurements to measure the force. But let's take a look at this picture, which you guys do have it down at the bottom there, okay? So first, let's say this hockey puck has a mass of 1 kilogram. It really doesn't. Hockey pucks don't weigh that much. But let's say for our purposes they do. If something is experiencing an acceleration of 1 meter per second squared, what did we say that means? If the acceleration is 1 meter per second squared, what has to happen? Is that a hand or is that kind of a fake hand? Okay. If the acceleration is 1 meter per second squared, what does that mean? What is? The object's velocity is increasing by 1 meter per second for every second. We should probably change one word in that description though, right? Instead of an object's velocity increasing by 1 meter per second, changes, right? So if we want to speed up this hockey puck from 0 to 1, we have to do it in 1 second. That's the definition, okay? How hard we would have to push in order to do that, that's the definition. Now, that makes no sense to you, right? That's absolutely nothing there, okay? But if we talk about it in terms of something maybe a little more practical, if we take an apple and you take it from the table and bring it up to your mouth in order to take a bite out of it, the force that you have to apply to that apple to do that is approximately 1 Newton, right? Obviously it depends on the mass of the apple and how hungry you are, like how quickly do you put it up to your mouth, like that, you know, that kind of stuff. But, okay, that's about 1 Newton, right? Which isn't very much force. I mean, if you consider that, you know, that's 1 Newton, think about how many newtons you would need in order to like launch a rocket or something like that, okay? But, so we'll talk about that more as we get there, okay? All right. What we find out is that of all the different things that happen out there in the universe, and while there are contact forces and field forces and stuff like that, when we boil it down, there are really a limited number of forces that get applied in different situations. So the first type of force is an electromagnetic force. We have discussed an electromagnetic force before. Electromagnetic forces exist between what? Charged particles, right? And tell me those charged particles come from? And electrons, right? So the forces between charged particles, positive and negative charges, or protons and electrons. And we learned that one of two things can happen. What can happen because of electromagnetic force? These charges can either So what can electromagnetic forces do? They can either attract or repel, depending on what kind of charges we're talking about. Electromagnetic force is unique in that way, in that it can be an attractive force or bring things together under certain circumstances, but it can also push things apart in other circumstances, depending on the charges, etc., etc. Good there. All right. And examples, right? We looked at a ton of examples when we were talking about the electricity unit, right? Protons and neutrons. We talked about, rubbing hair on a balloon or magnets. These are all application. Or electromagnetic induction, where we caused a current in a wire even though there's no battery attached to it. All these things, right? These are all examples of electromagnetic forces. Okay? And just for old time's sake, right? We can take a look at this girl again and her. Yeah. So I know you missed her. I mean, it was like before Christmas that we saw her. She's back. Yeah. So I think that might be like the author's daughter, maybe. And it's just like, here, rub this balloon on your head, okay? So, and smile. So, all right, good there. Do you want me to leave it up there for a little while longer, or? Printed out like big and glossy too, like not like a lame printer one. Like we need like a real, like, just take that baby to like Office Max or something, get it laminated. So. All right, the next kind of force we come across is something called the strong nuclear force. You may not remember, but we have talked about strong nuclear force in the past. If we think back to our third unit of the year, atomic theory. So we talked about atoms, right? And we talked about what an atom looks like. And we talked about that there are basically two parts to an atom. What are the two parts to an atom? The nucleus, and then the electron-y part, right? Okay, so there are two things in the nucleus, right? What are the two things in the nucleus? Protons and neutrons. All protons have a positive charge. What do they try to do to each other? They try to repel each other. So, in reality, the nucleus of an atom really shouldn't exist, because the protons should all push each other apart. But the nucleus of an atom does exist, which means there has to be something that holds protons together. That something is called the strong nuclear force. As we learn more and more about an atom, we realize that the neutrons that are in the atom actually play a role in holding the protons together. That's why they're there. If the neutrons weren't there, the atom would just fall apart, or at least the nucleus would. The strong nuclear force is a very strong force. But, sorry, I left some lines off there. I apologize. I actually found on the front that there was a line that was missing. I fixed it before I printed it out, but apparently it wasn't. The strong nuclear force is very strong, but when you pick up, your pencil, the strong nuclear force does not play any role in that. The only role that it plays is holding the atoms in your hand together and holding the atoms in your pencil together, because even though the strong nuclear force is very, very strong, it only acts over a very short distance, like the nucleus of an atom. other than the fact that they're just completely hypothetical. And we have no evidence to suggest that they exist. All right. The last force that we're going to talk about is one that you all know very well, and that's gravity. We know that gravity does what to objects? Well, it pulls them down, which is true here, but if you go on the other side of the earth, right, it actually pulls them the other direction. But more generally, it pulls things how? Or together, right? Gravity is an attractive force. It pulls things together. But it is an attractive force that exists between any two masses in the universe. So anything that has mass will feel gravity between anything else that has mass. So while we think of gravity as being something that pulls objects to the ground, in actuality, gravity is anything that gravity is something that attracts any object to any other object. While you are gravitationally attracted to the earth, and your pencil is also gravitationally attracted to the earth, and that's why if you let it go, it falls. But you are also gravitationally attracted to your pencil. You are also gravitationally attracted to the person next to you, or behind you, or in front of you, whatever, right?
So how big would it take for me to be like above you to start making me like
So, okay, so let's talk about this. So, Tyler brings up a good point. Tyler asked, how big would something have to be above you and gravitationally attract you? Is that basically what you got? So, the reason why this is a good point is because even though it dominates everything that we do here on Earth, gravity in by itself is actually a very weak force. Consider that if you have a balloon, rub a balloon on your hair, right? Stick it to the ceiling. You can make the balloon stick to the ceiling, right? While that balloon is sticking to the ceiling, the electromagnetic force between the balloon and the ceiling, the protons and the electrons, right, is stronger than the entire gravity of the Earth pulling it down. Does that make sense? Because it stays stuck to the ceiling. So the answer is you have to have a lot of mass to really make any kind of significant gravity. That's why if you drop something, it doesn't fall in a diagonal line and come closer to you as it's coming closer to the Earth. Technically it does, but the attraction of the Earth is so much stronger because its mass is so much greater that it just falls straight down, right? So the answer is a lot, right?
how annoying would it be if we like all had our own gravitational field?
Yeah, you know, now somebody asked that, they're like, if you got away from Earth, if you were the biggest thing around, you have your own gravitational field where you can affect other objects gravitationally. So the Earth has its gravitational field, and that gravitational field is strong enough to make the moon orbit around the Earth. In theory, you could have your own little orbiting system, like your cell phone and your keys could just like orbit around you, you know. That would be so. All right, hey, do we get these last two parts here? The strength of the gravity depends on two factors. One, it depends on how big the masses are. The bigger the mass of the two objects, the greater the gravitational force between them. But as those two objects get farther apart, the force of gravity decreases, an inverse relationship. Okay. All right, good there? Tomorrow we talk about how to make your mom not be mad at you if you sleep in until noon. Okay. Oh, there's some homework on the calendar tonight. Check it out. I'll move it to Tuesday because right now it's on Monday.